Alright, so we're going to take a look at a really quick pressure problem. And the problem reads, the two water reservoirs in the figure are open to the atmosphere and the water has density 1000 kilograms per cubic meter. The manometer contains incompressible mercury with a density of 13,600 kilograms per cubic meter. Find H if the manometer reading is 25 centimeters. So the reading is here is the difference between the height levels of the mercury. So we have here the given information. The density of the water is 1000 kilograms per cubic meter, and the density of the mercury here in red is 13,600 kilograms per cubic meter. So we're going to use, what we're going to do is we're going to apply the simple fact that a pressure change in liquid corresponds to the change in height. So the way we start this problem is we begin at the very top. So at the very top of this reservoir, the atmospheric pressure is what's acting on the water. So we have P atmospheric, and then plus the gauge pressure of the water. So that's going to be rho of the water times g, the gravitational acceleration, and times h1. So h1 is going to be the change in height from the top of the water all the way down to this point of contact between the water and the mercury. So if we go up, if we change our height from this level to this level, then the change in pressure is going to be a minus rho of the mercury, so that's the density of the mercury, times G, and then multiplied by the manometer reading, right? So this is going to be 25. So we have minus rho of the mercury times G times 25 centimeters. Now, of course, we can write the 25 centimeters as 0.25 meters. So let's write this as 0.25 meters. So 0.25 meters. And then we're also going to, once we change our height to this next point of contact, we're also going to include the pressure change going to the very top of the second reservoir. So in fact, let me shift this downwards here. Let me bring this down so we have a little bit more space to work with. So this height change is going to correspond to a negative change in pressure. We're going to have a minus rho of the water times G, and then times H2. So H2 is going to be the change in the water level from this point of contact to the very top of the second reservoir. So all of this must be equal to the atmospheric pressure acting on the top of the water level at the second reservoir. So this is P atmospheric. So these two pressures cancel out, which means what we have is rho of the water times G times H1 minus rho of the mercury times G times 0.25 minus rho of the water times G times H2. And this has to be equal to 0. Now, what we're looking for is H, the change in height here. So we can solve for that by transposing this this term over here that's due to the mercury. We can transpose it to the right side of the equation and write rho of the water times G multiplied by H1 minus H2 is equal to rho of the mercury times G multiplied by 0.25. Okay, so H1 minus H2 here is just H, the change in distance that we're looking for. So we can write rho of the water times G times H is equal to the density of the mercury times G times 0.25. And if we cancel out our G's, we find that H is equal to the density of the mercury divided by the density of the water, and that multiplied by 0.25. And if we plug in the values, we find 13,600 divided by 1,000 multiplied by 0.25, and this gives us 3.4 meters.